There is a lot of confusion about what exactly to prepare for system design interviews for data engineering. What are the kind of topics? What are the type of questions that are asked? And is it even the same as system design interviews for software engineering? So to be honest, most candidates study plenty. They've read a good amount of books, they've watched enough videos, but the reason why this round is hard isn't completely because of lack of knowledge. But of course, if you don't have the required bar of knowledge, you will fail by default. What I'm saying is that there are several candidates who still fail this round despite having good amount of knowledge. And it is primarily because it tests how you navigate ambiguity. In DSA, even the hardest problems have a solution. They have a destination. They have an answer, right? Uh, a two-pointer problem, let's say, has a correct answer. A dynamic programming problem has an optimal substructure. You break it down, you solve the subproblems, and then you arrive at the solution. You arrive at the answer. System design, on the other hand, is open-ended in a way coding questions aren't. And what I mean to say is that there is no correct answer. If you ask 10 different senior engineers to design the same ingestion pipeline, you are going to get 10 valid architectures, and each of it will be with different trade-offs, some on cost, the others on latency, complexity, failure handling. Yeah, so there is no optimal solution per se. You have to justify your choices, and that's why explaining trade-offs becomes very important. The interviewer isn't just checking whether you reached an answer or a solution, they are checking whether your reasoning holds up when they change some of the constraints. And changing some of the constraints can look something like: what happens when the volume becomes 10x? What happens when the business who was looking at the dashboard, they are now expecting it in 10 minutes instead of one full day? What happens when a source becomes unreliable? So this is where your preparation from software engineering system design interview resources, an example like URL shorteners, Twitter feeds, they are not going to work for data engineering system design interviews. The list of topics to cover for system design interviews is large. For example, ingestion patterns, data modeling choices, batch versus streaming trade-offs, schema evolution, idempotency, backfills, cost and scale. Yeah. But the way you approach any of these questions is going to be the same. So it's really important to note that the way you approach any of these questions is going to remain the same. Every data engineering system design problem, whether it's building a lakehouse for e-commerce, whether it's building a recommendation pipeline, a fraud detection pipeline, or a customer 360 platform, all of this can be broken down using the same single framework. Yeah. And this framework is exactly what we are building today. Hey everyone, I am Afaq Ahmad, Solutions Architect at Databricks and previously a Junior Principal Data Engineer. I work on a day-to-day basis with multiple companies designing and building massive data platforms serving millions of users. And I've also been on the other side of the table, having interviewed hundreds of candidates. So in this video, I am going to give you everything that you need in order to crack data engineering system design interviews. So for each of the topics, I'm going to tell you not just how to approach that topic, but also how to think like a senior engineer in that room. At the end, I am going to walk you through a real system design interview question that's been asked at companies like Uber and DoorDash, step by step, exactly how you would answer it in a 45-minute interview. So if you are preparing for a senior data engineering role at top tech companies, you should not skip any part of this video. So now let's get started. So before we dive into the individual topics, I want to give you the map. Yeah. So think of this as your mental framework you are going to carry into every single system design interview. Yeah. Regardless of the company, the domain, or the specific question that they are going to throw at you. So there are 6 steps and they work in order. So one must try to cover as much as possible from these 6 steps in the system design data engineering interview. So the first step is requirements gathering. Yeah. So basically, this is understanding the problem even before you draw a single box on the whiteboard. Yeah. So it is understanding more about the system that you've been asked to build. So you should ask questions around, let's say, who is the user who is going to use my system? What are the functionalities that it is supposed to offer, right? What exactly are the things that it is supposed to do? What are the latency requirements? And what I mean by latency over here is, let's say the end users, the who over here, are a set of people from the marketing team who want to look at a particular number of dashboards, right? 3 to 5 dashboards. So we need to check with them whether 5 minutes of latency is something that they need, or they are good with 1 day of latency with the data being refreshed on a day-to-day basis. What is the volume of data that we need to process, right? Is it in megabytes? Is it in gigabytes? Or is it in petabytes, right? So knowing all of these facts is drastically going to influence and impact our decisions downstream when we design our pipelines, when we design the overall system. So that is something that you will see down the line. Number two, the second part that we should cover is pipeline design. So how does data move from a particular source to a particular destination, right? If we are ingesting data from somewhere, how does it move from that source into our destination, right? What is the mode of operation that we are going to choose, which is either it is going to be batch or is it going to be streaming? What is the architecture that we are going to choose? Is it going to be Lambda, or is it going to be Kappa, or is it going to be Lakehouse? Is it going to be the Lakehouse architecture? Which tool are we going to use for orchestration? Yeah, so there are several tools in the market, which is, let's say, Airflow, Prefect, Dagster, or Mage. And is there a preference towards any of these tools? The third step is data modeling. This is basically deciding how does the shape of our data look like, right? How does the table structure, medallion layer, slowly changing dimension, all of this is going to look like. So are we going to go ahead with a star or a snowflake schema, right? How are our fact and dimensions? How are our fact and dimensions going to look like, right? How, if we are going with a medallion layer, how are our bronze, silver, and gold layers going to look like? Yeah. Where is this fact and dimension going to reside? Is it going to be in the silver layer or in the gold layer? Where exactly it is going to reside? So in most cases, the data model is in the silver layer, and then you build aggregated tables, aggregated metrics in the gold layer. And given that we have dimension tables over here, we will also need to think about things like slowly changing dimension. Which one are we going to follow? Is it going to be type 1, 2, or 3, right? Based on the requirement. I want to take a moment to talk about Educative, who is also sponsoring this video. So Educative is a fully interactive text-based learning platform, and they've integrated several diagrams and visual explanation, which makes learning a lot easier and interactive. Their legendary grokking the system design interview is one of the most widely used resources by thousands of learners preparing for interviews at Google, Meta, Amazon, and many other big tech companies. So it really starts with building your foundations with the functional, non-functional requirements, back of the envelope calculations, things like load balancer, databases, caching, right? And it gets your foundation right. Yeah. And then it walks you through more than 13 real system design examples that have appeared in actual interviews. If you want to go deeper, the advanced system design interview prep crash course covers the senior level harder scenarios, and grokking the low level design interview using object oriented design principles is actually a fantastic resource for the object oriented design rounds, where they start with the object oriented design principles and then they go deep into design patterns together with solving real world examples. Like, for example, design a parking lot, design a ride sharing system, an elevator system, Amazon locker service, and many others. Yeah. So together these three pretty much cover every system design interview you are going to run into. Beyond the system design path, Educative now has a full generative AI learning path with courses like Mastering the MCP, Cursor AI for Enterprise. Cursor AI is something most of us use on a daily basis. Agentic system design and Claude code workflows. Yeah. So exactly the stack you need to stay ahead right now. And finally, if you prefer learning on the go, Educative Go lets you continue lessons, run code, and practice quizzes right from your phone. So right now, Educative is running a massive 67% discount. So claim it while it lasts. You will find the link in the description below. And now let's get back to our topic. Number four is storage and file format. So basically, where does your data live and in which format does it live? Is it in Parquet? Is it in Avro? Is it in Delta? Or is it in Iceberg? And what is the storage optimization strategy that we are going to follow? So there are storage optimization strategies like partitioning, bucketing, and liquid clustering as available on Databricks. So which of the strategies are we going to follow for optimization? Yeah, and this is drastically going to have an impact on cost. Yeah, the next step is basically on data quality and observability. So how do you know that the outputs that is being produced by our pipeline, they are healthy and they are correct? So this is basically by setting up certain data quality rules and metrics in place, which can help you make the decision. Yeah. And there are other things like testing, monitoring, alerting, SLAs, which are going to form the trust, for our data pipeline and infrastructure that we are going to build, right? So they are going to build the trust on the design and the pipeline that we are going to build. Yeah. Lastly, we are going to talk about scalability, backfills, and data ops. So can this system handle 10x the load? So what happens if something breaks? Are we able to handle failures gracefully? Are you able to reprocess 3 months of data? Yeah. Is your pipeline idempotent? When you run it multiple times, does it behave in a consistent fashion? Yeah. So these 6 steps form the core for a data engineering system design interview. Now, here's the thing about interviews. Interviewers use a wide and then zoom approach. So they'll start with a broad question, something like design a data pipeline. So design a data pipeline which basically tracks user activity. Yeah. So which basically tracks user activity for an e-commerce platform. Yeah, which basically tracks user activity for an e-commerce platform, and then they are going to drill down into 2 or 3 or as many amongst these 6 topics, these 6 steps over here. Yeah. So all right, let's start with step one, requirement gathering. I would say that most candidates rush through this step. Yeah, we basically get overly enthusiastic and we start building boxes on the whiteboard. So let's take a step back. Always focus on requirement gathering. Try to understand more about the system that you're trying to build, because this can seriously cost you the entire interview. So please pay attention on the first step as we are going to study it. So here is the scenario. Let's assume that the interviewer tells you design a data pipeline to track user activity on an e-commerce platform. Yeah, and trust me, I've seen this happen. Most of the candidates jump straight to the whiteboard and they would start drawing boxes with Airflow, Kafka, Spark on it, right? Don't do that. Don't start designing a system without fully understanding what it is supposed to do, right? What are you supposed to build? Yeah. Take a step back, spend the first 5 minutes doing something really very simple, asking questions. So requirement gathering is the most underrated step in the entire framework, and it is a very simple step that immediately separates strong candidates from the average ones. So there are 2 types of requirements that you need to nail down, and they are functional and non-functional requirements. Yeah. functional and non-functional requirement. So what exactly is functional requirement? Functional requirement means that what does the system need to do? The system that we are building or designing, what does it need to do? And how do you figure this out? How do you answer this question? So the first thing that you start with is with the end user. You start with the who. Yeah, you start with the end user. You start asking questions that who is the end user who is going to use or consume from the system that I'm going to build. So is it a marketing analyst running SQL? Is it a marketing analyst who is running SQL, right? Or is it an ML team which is feeding data into a feature store for their recommendation engine? So is it an ML team, or is it a product team monitoring real-time product metrics, right? Or is it a product team monitoring product metrics, right? The reason why this question is really important to be asked, because this is going to tell you the kind of architecture that you're going to build. Because if we look at these three users, the architecture is going to look completely different. So marketing analyst, for this one, it can simply be a bash architecture, whereas for these two, it has to be a streaming architecture, right? So that's why the first question that you need to ask is who. Yeah. The second question that you need to ask is what do they actually need? Yeah. So the second question you need to ask is what do they actually need? Do they need aggregated metrics? Do they need raw level events? Or do they need historical snapshots, right? Or do they need historical snapshots? Yeah. So this is the second question you need to ask. And the third question that you need to ask is how are they going to access it, right? The how. How are they going to access it? Is it directly through SQL queries? Is it directly through SQL queries, or is it through, let's say, a BI tool like Tableau or Power BI? Yeah, or is it through REST APIs? Yeah. So let me take a concrete example and tell you how functional requirements are going to look like. So let's take this example for the marketing team. The marketing team basically needs to understand how users move through the purchase funnel. Yeah. So if you are on an e-commerce platform, the first thing that you would come would be the homepage, and then let's say you search for a particular product, you view the product, you add the product to cart, and you finally purchase the product, right? So let me show you how the funnel look like. This one, let's say, is the home page, and then you search for a product, you view the product, and then if you like the product, you add it to the cart, and then the product is finally purchased. Yeah. Now, they would want to look at different metrics at each of these stages. And some of these metrics can look like this, right? So let's say there are 100,000 users who visited the homepage. And then there were 60K users who finally came to search product page, which means that there is a 40% drop off. And from here, 30K users came to actually viewing the product, which is a 50% drop off, higher than what it was earlier. And once a person has viewed a particular product, only 10K users came to the add to cart page, finally added to cart the product that they were viewing, and this is a 67%, a much higher drop off. And finally, only 4K users purchased the product, which is 60% drop off, right? So here it tells us the journey of the user right from starting from the home page, starting from the home page to purchasing the product. Yeah. And the marketing team would definitely like to slice and dice these numbers by certain dimensions, right? And what can those dimensions or segment look like? So for example, one of them can be user type. Is it a new user? or is it a returning user? Is it a free user or is it a paid user, right? So they would want to see that what is the purchase rate of new users versus returning users, and is there something that they can do about it after reading through the metrics. Yeah. The other dimension that they can segment by is device type, right? So let's say the conversion rate across desktop is, let's say, 2%, while on mobile it is 6%. Yeah. So this could also signify that the checkout flow across desktop might not be so seamless, or it might be broken. Yeah. So this could make them look deeper into the problem statement and then resolve the problem. Yeah. So this basically gives us an idea about the problem that the marketing team would want to solve. So what is the functional requirement from here? The functional requirement is basically the functional requirement from the marketing team would be that they want to look at funnel metrics. Yeah. Funnel metrics at daily granularity, segmented by dimensions, and these dimensions can be, for example, user type, this can be device type, and then there could be several other dimensions that could come in, right? And this has to be accessed in Tableau, right? So this is something that we need to come up with after talking with the interviewer, or let's say when we do problem solving, day-to-day problem solving in real life with business stakeholders, and understand that this is the functional requirement for the system that we have to build. So the next one now is non-functional requirements. Yeah, which basically means how should our systems behave? Yeah. So can it handle 10 terabytes of data? Can it refresh within an hour? Yeah. So there are some key areas which we should always dig into whenever we are talking about non-functional requirements. Yeah. So the first key area is latency SLA, which simply means that does your data need to be fresh within a minute, or is 1 hour acceptable? Yeah. So if an hour is fine, then you're looking at a batch architecture. So if an hour is fine, if you're then you're looking at a batch architecture. Yeah. If a minute or less is the requirement, right? Less than 1 minute, then we are looking at streaming. Yeah. Then we are looking at streaming. So the infrastructure cost, the complexity, operational overhead, all of it is then going to go up. Yeah. So this one answer alone can change the entire design. So that's latency SLA. The second one is volume. So are we ingesting 1 gigabytes of data a day or 10 terabytes of data a day, right? Are we ingesting gigabytes of data a day, terabytes of data a day, or petabytes of data a day? So this changes every storage and compute decision we make. So at 1 gigabytes of data a day, you can simply get away with a single node tool like pandas or polars. Yeah. But if we are talking about terabyte or petabyte scale, then you need distributed compute like Spark. And not just distributed compute, you also need a serious storage optimization strategy like partitioning, bucketing, or let's say liquid clustering. Yeah. So that the queries don't end up scanning the entire data set. The third one is availability. Availability simply means how much of tolerance do we have for downtime? Yeah. Can we tolerate 10 minutes of downtime during a production deployment? The last one is data retention, which simply means do we keep everything forever, or do we move records to the archive layer after 90 days of usage, right? So do we keep the records forever, or do we move the record to the archived layer after 90 days of usage in order to optimize storage cost. Yeah. So these are the four areas that you should definitely touch and speak about whenever we are clarifying and trying to freeze our non-functional requirements. Now let's get back to the original question. Design a pipeline to track user activity on an e-commerce platform. So here is how the same vague question leads to two completely different answers just based on the requirements alone. Yeah. So let's take two different scenarios. The first scenario is that of the consumer is a marketing team. They want daily reports on the user behavior, as I mentioned earlier, which pages the people visited, what products were added to the cart, and how the conversion funnel looks like. Yeah. So they query this in Tableau and they can wait 1 hour for the data to be refreshed. Yeah. So this is a classic batch pipeline. Yeah. So this is a classic batch pipeline, your Spark jobs, Airflow orchestration, Delta tables, a data model with facts and dimensions. Now let's take the other scenario number two, where the consumer is an ML team serving real-time product recommendations. Yeah. So every user action needs to be updated in the model's feature store within seconds. Yeah. So think of Uber Eats showing you trending restaurants right now, or DoorDash re-ranking the results based on what you browsed just 30 seconds ago. Yeah. So in these cases, the user's actions need to flow into an online feature store within seconds, and then the model reads those fresh features at inference time. So this is a streaming architecture. Yeah. Kafka, Splink, or Spark structure streaming together with Delta table, feature store, completely different system, right? So you see the question is the same, but it leads to two different design. Yeah. The requirements are what determine the answer. So it's really important to focus on requirements gathering and trying to ask as many meaningful questions so that we are able to arrive at the right architecture. Okay, now here is something I've seen instantly elevates your answer, right? Once you've gathered the requirements, do a quick back of the envelope calculation, right? So do a quick back of the envelope calculations. Yeah. And I'm going to tell you what exactly this means. Yeah. So the reason why I am asking you to do this, and I see most candidates skip this entirely. So this is basically going to tell the interviewer that you don't just talk theory, you also think in numbers. And those numbers are the ones which is actually going to drive design choices, design decisions, and we'll see how. Yeah. So let's do one together. We will stick with scenario A. We will stick with scenario A, and basically scenario A was the batch pipeline for the marketing team. They want daily reports on user behavior, page views, add to cart action, conversion funnel, refreshed every hour and queried in Tableau. Yeah. So the first thing that we are going to start with is the users, right? So let's say that this e-commerce platform has 5 million daily active users. Yeah. And when you assume these numbers, do it back and forth in discussion with the interviewer. Ask them whether this number looks reasonable or not. And then based on the discussion, tune these numbers, right? So that it seems that this is a continuous discussion, right? A design discussion between you and the interviewer. Yeah. So let's assume that this platform has 5 million daily active users, and each user is going to generate 30 events per session. 30 events per session. Yeah. And each of these events, what do these events mean? These events are basically things like page clicks, page views, clicks, searches, add to cart. Yeah. And let's also assume that on an average, On an average, the number of sessions per user equals 2, right? So there are 5 million users. Yeah, each user does 30 events in a day on an average, and each user has 2 sessions, right? So let's assume that you log into amazon.com twice in a day on an average, and you, let's say, view a particular product, see more details about a particular product. If you want to buy it, you add to cart and then you purchase it, right? So this is how some of the metrics look like. And again, as I said earlier, talk through with the interviewer, discuss this, whether these numbers make sense or not. Yeah. So in order to calculate the total events per day, now we are going to calculate total events per day. It is simply going to be 5 million users, and 5 million users on an average do 2 sessions in a day, and each session is 30 events, right? So this is going to be 300 million events in one day, right? So it is going to be 300 million events in one day. Now let's try to estimate how much is going to be the size of these 300 million events, right? So what is an event going to contain, right? So let's assume that one event is going to be one JSON, and it is going to contain something like, let's say, the user ID, session ID, yeah, event type, the timestamp, the page URL, basically things like this, right? So one event is going to contain all of the detail, and let's assume that this event is roughly going to be somewhere between 500 KB, 500 bytes, not kilobytes, 500 bytes to 1 KB. Yeah. So on an average, let's settle down on a middle number, which is 700 bytes, right? So the size of one event, we are assuming it to be 700 bytes. Yeah. So now if we want to calculate the size of all of the events, the size of 300 million events, 300 million events, which is the size of 300 million events, it is going to be 300 million into 700 bytes. Yeah. So this is 210 gigabytes per day. Yeah. And if you're looking at what is the monthly number, just multiply it with 30, it is going to give you 6.3 terabytes per month, right? So this is the volume of data that you're working with. Yeah. And these numbers matter because they directly tell you what you should build and what you shouldn't. Yeah. So at 210 gigabytes of data per day and 6.3 terabytes of data per month, we are dealing with distributed processing tools. Yeah. So we are dealing with distributed processing tool. A single node tool like pandas or polars is not going to work. Yeah. So that is why we have to use something like Spark in order to handle this volume of data efficiently, right? So that's the first thing. Based on our calculation, we figured out that we need Spark, we need distributed processing in order to handle this volume of data. And for storage, if let's say you are retaining 12 months of data, 12 months of data in your bronze layer, then basically we are talking about, let's say, 6.3 TB per month into 12, which is roughly 75 terabytes of data in a year, right? So we are basically generating 75 terabytes of data in a year, and this is before compression. Before compression, yeah. If we use Parquet, or let's say Delta Parquet, the Delta format, Uh, then we are talking about roughly 2 to 5x compression, and this is going to be roughly somewhere between 15 to 38 terabyte of data, right? And this is again very manageable storage on top of S3, right? This is not a lot, but you need a very good storage optimization strategy. And the first thing that you can start with is, of course, something very simple like partitioning. So we have all of the events coming in. You can simply partition by the event date, and then it can be something like dd, right? So for per day, you can partition by event date so that the hourly batch jobs scan only the data that they need instead of the entire data set, right? So the marketing team is querying INTERVEW with an hourly refresh SLA. And with this, you don't need any streaming infrastructure at all, right? So we've seen and understood with this calculation that we don't need any streaming infrastructure because of some of the requirement gathering that we did earlier. Every day of refresh is fine, and therefore we don't need any Kafka, Flink, or any of that, right? A scheduled Spark job running through Airflow is good enough. Yeah. So with this calculation, so to quickly summarize, with this calculation, and let me change the color over here. So with this calculation, where we first calculated what are the number of users on our platform, right? What do they do on the platform? Like what are the average number of events that they fire in one session? And we found out that we settled on a number that it is 30 events per session. On an average, they do 2 sessions in a day, and this leads to 300 million events in a day. Then we estimated what is the size of those 3 million events. Yeah. We said that one event is going to be one JSON, which is going to look like this. One JSON is 700 bytes of data, and therefore 300 million events is going to be 210 gigabytes of data in a day, or 6.3 terabytes of data in a month. So this tells us that pandas and polars is not good enough. We will have to use Spark. Yeah. And coming to the storage decision, if we want to store 12 months of data in the bronze layer, we are talking about roughly 75 terabyte of data before compression, and 15 to 38 terabyte of data after compression if we are using storage formats like Delta, or simply Parquet, right? And we also need to partition our data set by event date so that we don't end up scanning the full data sets, right? So we also settled on a storage format which is Parquet or Delta, right? So we see that with this simple math, we have made four major decisions. Yeah. Number one is the compute engine. About pandas, polars, and Spark, we are going to choose Spark. About the storage format, which is Parquet or Delta. About the orchestration tool, based on the need from the marketing team, that they are good with daily refreshes, so we are going ahead with Airflow. And we also ruled out an entire category of streaming infrastructure, right? So you get a glimpse of how important this back of the envelope calculation is, and it gives you so much of leverage and so much of power during the interview. Step 2 is pipeline design, and every interviewer is going to ask you some version of this question, right? So how are you going to move and transform the data from source A to destination B? Yeah. And your first job is to figure out, are we doing this in batch or are we doing it in streaming, right? So this is the first thing that you must figure out. Yeah. So let's break down both. Let's first study about batch processing. So batch is what runs 90% of the pipelines and the workloads almost everywhere, right? So you use it when the data doesn't need to be fresh every second. So if you think of it, it can be hourly reporting, daily analytics, or anything where the cost matters more than latency, right? Where the cost matters more than latency. Yeah. So your standard stack over here is Spark, Apache Spark for the heavy lifting, Airflow prefect or Dagster to be able to orchestrate the whole pipeline. Yeah. And the whole pattern looks like you have a source, and then you basically extract data from here. Yeah. And then you land it into, let's say, an object storage, which is S3 or ADLS. And inside of this, it is going to go through different layers where we call it the bronze, silver, and gold, right? It goes through all of these different layers. And then this is finally served on to a dashboard. Yeah. So let's take a concrete example. So here we have an e-commerce company which needs daily sales report. Yeah. So there is an Airflow DAG, this Airflow DAG, which orchestrates the whole thing over here. It basically runs at 2 a.m. at midnight. Yeah. So the Airflow DAG kicks off at 2 a.m., basically pulls up the data from this Postgres database over here. Yeah. And then it basically lands, it extracts all of the data, and then it lands all of this in the bronze layer. Yeah. So a Spark job basically takes up all of the data from here, and then it does all kind of cleaning, transformations, and it puts it into the silver layer. Yeah. And then another job basically takes the data in the silver layer and then puts it into the gold layer by aggregating things, right? By aggregating, slicing and dicing the data by, let's say, the product, region, and then puts it into the gold layer. Yeah. So let's say by 6 a.m. the data is ready, and then it is connected to the Tableau dashboard, which gets refreshed with fresh numbers, right? So this is batch. It is nothing fancy, but it powers most of the dashboards that you use on a day-to-day basis. Now, what if waiting until 2 a.m. is not an option, right? So we took this example over here where our DAG ran every day at 2 a.m. It completed at 6 a.m., right? So what if waiting until 2 a.m. is not an option? So in that case, we use stream processing when we need low latency, right? When we need low latency. So here I explained earlier that batch becomes very relevant when cost is greater than latency, right? When cost is much, much more important than latency. But in streaming, latency takes preference, right? And what we desire for is low latency, right? So we need things like real-time dashboards, fraud detection, event-driven systems, or anything with latency SLA under a minute. Yeah. So basically your stack over here is Kafka for ingestion, right? Kafka for streaming ingestion and buffering, and then Spark structured streaming or Flink for processing, right? So Spark structured streaming or Flink for processing. And then all of this data goes into either Delta Lake for storage, right? Delta Lake for storage, and this is basically for the historical layer. This is basically for the historical analytics layer, and a serving layer like Redis or DynamoDB or Cassandra for low latency real time needs, right? So something like Redis or DynamoDB. Yeah. Okay, here is how it works. So your source system, it could be an app, it could be a website, it could be transactional databases, right? So every click, every transaction, or every status update, those events are going to be pushed into Kafka. Yeah. So these events are going to be pushed into Kafka. Yeah. So Kafka is going to act as the buffer over here. And Kafka basically decouples the producers from the consumers. So events are basically retained in Kafka for a configurable period. It can be days, it can be weeks or months. And then consumers are basically going to read at their own pace using the offsets, right? So now our stream processor is going to read the data from Kafka in real time, in near real time, right? And this stream processor can be either Spark structured streaming or it can be Flink. Yeah. So this is basically going to either, let's say, enrich the events which basically came from Kafka. Yeah, with another source, or basically filtering out what's not needed. Yeah, so the processor does its work and basically it writes the result to a serving layer like Redis or DynamoDB that needs to be instantly read by, let's say, an app or a live dashboard. Yeah, so this is how the flow is going to look like. Now let's take a concrete example for a ride hailing company, and we basically say that, let's say we take an example of a ride sharing app which needs to show drivers in real time their earnings as they complete the rides. Yeah, so once every ride is completed, the event gets pushed into Kafka. So once the ride is completed over here, once the ride is completed, the ride completed event is generated, and this is basically pushed to Kafka over here. Yeah. Now that event which gets into Kafka, it basically carries details like, let's say, the fare, the surge, and what is the driver ID and all of that, right? Now Spark structure streaming is going to read this event. It is going to consume this event, and it is going to enrich it with, let's say, the driver metadata from a lookup table, and it calculates the running total for that driver, right? So it is going to enrich it with, let's say, driver metadata, and it calculates the running total for that driver ID. Now once it has done that, it simply writes the result, which is the earnings, into the serving layer, which is Redis in this case, and this is read by the app. Yeah. So this is how the result gets written into Redis so that the driver app can pull up their earnings instantly. Now, what if you need both historical batch data and real-time data in the same system? So that is where Lambda and Kappa architecture both come in. Yeah. So Lambda architecture basically runs two parallel paths, right? This is the first one and this is the second one. So your data comes in. This is where your data comes in. Yeah. And it splits into two. Basically, the first one is the batch layer that processes the historical data set, right? So this layer, it processes the historical data set, right? And then the speed layer, which handles real-time data as it arrives, right? So this one basically handles real-time data as it arrives. Yeah. So both paths, they are going to write to a serving layer. Now the serving layer can either be common or it might not be common, right? And we'll look into a few examples, but overall, this is how a Lambda architecture is going to look like. Okay, so let's take an example to understand this. So think about what a ride hailing app needs to do simultaneously. When you open the app and when you tap request a ride, your phone, basically the app, sends an event to a streaming service like Kafka. Yeah. So in this case, we've taken the example of managed streaming service for Kafka on AWS, right? So the moment you open the app, you click on request a ride, this event is pushed to Kafka. This event is basically pushed to Kafka. Yeah. So from here, two independent consumer groups read the same event simultaneously. And those two independent consumers are, number one, the streaming group over here. And then you have the batch group over here. Yeah. So these are the two consumer groups. Now, Flink, which is the first consumer group, it is going to read your request for a ride within millisecond. Yeah. So this is basically going to read the ride request within millisecond. Now, what is also happening in the background is that several drivers, right, based on their location, they are also sending pings to the managed streaming service, right? So basically, they are going to send information about the location where they are, right? So then only the matching of me requesting for a ride to different drivers who are nearby can be made, right? So the driver pings are also coming in over here, and they are also going over here to the first consumer, right? So then this consumer is going to run an algorithm. It is going to run a simple calculation which calculate the search pricing for my area, and then it is going to write two different results to Elastic Cache, right? It is going to write two different results to Elastic Cache. The first one is going to be the fare details, and the second one is going to be the driver details. So this is going to be something like, okay, your fare is going to be 330 rupees and driver X is arriving in, let's say, 4 minutes. Yeah. Now all of this will happen within a few seconds of you requesting the for request ride on the app, right? So this is powered by the first layer, which is the streaming service. Now, of course, I'm simplifying the steps. The real steps are going to be more complicated, but this is to give you an inspiration, an idea about how things are going to work like, right? Now, the second consumer is AWS Data Firehose. Yeah. And AWS Data Firehose is basically a streaming, ingestion, and delivery service. So its job is to read the ride events. Its job is to read the ride events from MSK and flush it to S3, right? So it is going to flush it to S3. Yeah. So it doesn't process the data, it simply buffers it along with thousands of other events and it flushes it to S3. So your ride request is now permanently stored as it was produced in S3. Yeah. Now, another interesting thing to note is that Firehose over here has no idea what the streaming layer is doing, what Flink is doing. So if Flink goes down for a deployment, Firehose still keeps writing to S3 without interruption. So we've created two different layers. One is the streaming layer, the other one is the batch layer, and they keep working without interfering or being worried about each other. Yeah. So now once the data has landed in S3, Airflow is going to trigger nightly jobs, right? And this is basically to compute metrics that cannot be computed with real-time data and something that needs historical context. Yeah. So you can envision something like a bronze, silver, and gold layers on top of S3. And EMR, which is basically managed Spark in AWS, EMR is basically going to read the raw data in bronze layer, right? It is going to read the raw data in the bronze layer and then process it through silver and gold. So some of the example metrics that it is going to compute, some of the business problems that it can solve are answering questions like which pickup zones have the highest demand on Friday evenings between 6 to 9 p.m. Yeah. Which routes have consistently 3x higher cancellation rate, where drivers should be pre-positioned 2 hours before a cricket match at Wankhede Stadium ends. Yeah. So these are batch views, heavy in aggregations over historical data. Yeah. So now the serving layer is basically combines the signals from both the batch and the speed layer, right? So it basically combines the signals from both the batch and the streaming layer. So the real time views, right? The streaming layer is accurate for what is happening as of this moment. Yeah. The bash layer provides the baseline, it provides the historical context, but neither of them is sufficient alone. Yeah, the reason for that is real time data is noisy and it has no historical context. Batch data is accurate, but it is already stale by the time I want to use it. Yeah. So batch data got updated yesterday, but I want to know the state of something as of now. So it has already become stale by the time I want to read it. Yeah. So together they provide the ride hailing app a very grounded and current view. So for example, think of something like surge estimate. So when you open the app tomorrow and request a ride, the app just isn't reading from one place. Yeah. So it is reading from this elastic cache over here. Let me quickly change colors. It is reading from this elastic cache over here. Yeah. And then it is also reading from the batch layer over here, right? It is reading from the batch layer over here. The elastic cache, which is the speed layer, answers for right now. An example could be there are 47 ride requests in Bandra and only 12 available drivers. So the surge is somewhere around 1.8x, for example, right? And from the batch layer, historically, Friday evenings in Bandra between 7 to 9 p.m. have an average of 2.1x surge. Yeah. So based on these two numbers, we can make a more grounded estimate on what the actual surge could be. So this is a real example where we can use both of the layers in order to estimate a realistic search. Now let's talk about Kappa architecture. So Kappa architecture says why maintain two systems, right? Why maintain the streaming path over here and then the batch path over here? Just use one streaming path for everything. Yeah. So just use one streaming path for everything. Every event is going to flow through this single pipeline. And if you need to reprocess historical data, you just replay it from Kafka through the same pipeline. So one code base, one set of logic, and much simpler to operate. Yeah. So in Kappa, Kafka becomes your storage, and that is the key difference between Lambda and Kappa architecture. So Kafka, the key point over here is Kafka is going to become your storage. Yeah. So Kafka isn't anymore a temporary buffer through which events are going to pass through. You are basically going to configure it to retain data for days, weeks, or even months. So Kafka becomes both your ingestion layer and also your historical data store. Historical historical data store, right? So here is how it's going to work step by step. So every event is going to flow into Kafka and it is going to stay there. So every event, this can be an event from an app, from let's say a transactional database CDC change, or from IoT device. It is going to flow into Kafka and it is going to stay there. Yeah. So let's say you set a retention period of 30 days. Your stream processor, which is let's say Spark structured streaming, is going to read data from Kafka continuously, process events in real time, and then it is going to write the data into the serving layer, which can either be Redis or DynamoDB, yeah, or anything else, yeah. So now let's say so first of all, this is how the basic structure and architecture for Kappa looks like. Now let's say you want your business logic changes down the line, and you need to reprocess last 2 weeks of data with the new logic. So in Lambda, you would have a separate batch job. It is going to take, first of all, it is going to merge the new code and run all of the pipelines for 2 weeks using the new logic, right? In Kafka, you don't have a separate batch system. Instead, what you do is you create a new consumer group in Kafka. So in Kafka, we are going to create a new consumer group, let's say C2 over here, right? And point it to the offset 2 weeks ago. So this is going to point to today minus 2 weeks ago, right? So that is the offset that it is going to point to. Yeah. And basically we are going to replay those events through the streaming pipeline. So Kafka streams those historical events through the processor, and we are going to have a separate processor for replay. It is going to stream all of these events through the processor as if they are happening again, right? So once the replay catches up to the present, you can swap the output and you're done. So basically, once all of this data is ingested, this becomes inactive, this becomes inactive, and this is the one that becomes live, and then we are done. Yeah. So the limitation here is if you need to reprocess 6 months of data, Kafka has to either retain 6 months of data in storage, which gets expensive, or you've already lost that data because let's say you've not have had that much amount of a retention period, right? So replaying millions of events through a stream processor that's designed for continuous small batch processing, it is going to work, but it is going to be much slower than a Spark job that can read all of this data parallelly and process it in smaller amount of time, right? It will work, but it is not scalable. So that is why most companies today don't go for pure Kappa. They land the data both in Kafka and in S3 or ADLS for historical processing, which is essentially the Lakehouse approach. And I'll leave it for you as homework to read more about the Lakehouse architecture. All right, step 3 is data modeling. Now, most of you feel pretty comfortable drawing out the tables for data modeling, right? It's easy to draw out the fact tables, dimension tables, the medallion architecture, which is simple, bronze, silver, and gold. But in the interview, they don't just ask you to design a data model, right? They are going to push back on it. For example, why not denormalize this? What happens when this dimension changes? How does this perform at scale? Yeah. So it is not just about drawing tables, facts and dimensions, figuring out primary keys, foreign keys, and all of that, right? It's much more to that. So here are four things that you need to understand really well. The first one is, of course, the medallion architecture in depth. The second one is star schema versus denormalization. The third one is slowly changing dimensions, mostly SCD 1, 2, and 3. Yeah. And finally, partitioning and other optimization strategies. Yeah. So, first of all, let's start with the medallion architecture. The medallion architecture basically is a layered approach to organizing data in your lakehouse, right? And there are three layers: simply bronze, silver, and gold. Yeah. So bronze is basically raw data. So let's say this is all your data sets over here, right? This is your data sets residing in this PostgreSQL. All of this data is going to be ingested as is in the bronze layer, as is in the bronze layer, right? So you ingest it exactly how it is coming from the source, your JSON dump or CDC logs, right? So your JSON dumps or the CDC logs, they are going to be put in the bronze layer as it is, right? And these can be again JSON dump, CDC logs, raw API responses. You don't transform it, you don't clean it, you store it as is. Now, if something goes wrong downstream, you can always come back and reprocess it in the bronze layer, right? So that's the philosophy behind bronze layer. Now, silver is cleaned and structured. So this layer is basically cleaned and structured, right? So this is where you parse these JSON that has come in and you enforce schemas, you do things like deduplicating records, typecasting, and all of that, right? So there are a lot of examples where people build the dimensional data model. Your fact and dimension tables live in this silver layer over here, right? So this is your trusted source of truth for analysts and engineers. Now finally, gold layer is basically they are pre-aggregated, pre-joined data sets that has metrics that the analyst can query directly, right? So let's take a concrete example. Imagine you are building this for Spotify, right? So the bronze layer is going to contain the song played event. So this event that you see over here is a song played event JSON, right? So this basically every event is going to have, let's say, things like a timestamp, what is the user ID, what is the song ID that was played, for how much duration was it played, on which device was it played, what is the app version, right? And similarly, this is another event over here. Yeah. So this is how one of the events from Spotify is going to look like. But we must keep in mind that between different versions of the app, so we see that this is one version of the app. Between different versions, there might be a schema shift. There might be nulls coming in for certain fields and column. There might be duplicates that might come in, right? The second part over here is the silver layer. And in the silver layer, we are going to have our data model, and for this case we are simply going to have fact streams and dim song. So fact stream is going to record your user ID, song ID, when was it played, for how much duration was it played, and the device type. So it's going to read this JSON and then process it and then put the data in this fact stream table and the dim songs table. The dim song table is going to contain detail about the songs, which is the song ID, title, artist, genre, release year, and all of that, right? And finally, the gold layer is where your pre-aggregated, pre-joined data sets live. And in this case, this is going to be daily artist streams. So this is going to tell me for a particular artist ID and for a particular date, what were the total streams and what was the unique number of listeners. So we take all of this one and this one, we join it, aggregate it, and then create this table over here, right? So this is one table, fast queries, no complex joins required specifically over here because you have already aggregated this over here, and that's the purpose for the gold layer. Now the next topic is star schema versus denormalization, right? So you'll hear this debate a lot of times. You'll hear this debate a lot of times, asking whether we should use star schema or snowflake schema or one big table, right? So I'm considering star schema as the normalized option and comparing it with the denormalized option, which is one big table. Yeah. So star schema basically means you separate out your facts from your dimension. So let's say we have orders, we have customers, and we have products. So we separate all of this out into different entities, right? So orders becomes fact orders. We have a separate table for orders, which is fact orders. Similarly, for customers, we have dim customer, and for products, we have dim products. And BI tools love this approach. They are optimized to work with star schemas. It is normalized, easier to maintain, and the query performance is really strong when your joins are indexed very well. Yeah. The second one is the denormalized approach. Now in denormalization, and in this case we are referring to OBT, which is one big table. Yeah, one big table. So one big table simply means that you pre-join everything into a single wide table. So basically all of this, right? Orders, customers, and products, we basically join all of this into one single table, and that single table is called the OBT orders table. So it contains the orders detail, it contains the product details, which is category over here, and it contains the customer level details, right? So this is what pre-joined table means, right? So we pre-join everything into a single wide table, and it removes the join complexity for downstream users. Yeah, OBT shines really well when you have a specific well understood query pattern and you want it to be fast as possible. So think of a metrics dashboard where the product teams always query revenue by region and by product category, right? So they query revenue by the region and by the product category over here. Yeah. Over, and let's say they do this over the last 30 days. Over the last 30 days, right? So the same query every day, 20 different people, instead of making 20, all 20 of them hit a 5 table join, what we do is we pre-join everything once in our pipeline and give them this single flat table, right? So the scans are fast, there are no shuffles. So a star schema would mean joining 5 tables for them every time they are querying. So this is one of the biggest advantages, but of course there are downsides as well. Say, let's say that the product category that we have over here for a group of products changed. So let's say clothes change to apparel, right? Now, if we are using the star schema approach, we just need to change this one row over here, right? We just need to change this one row and we are done. But in OBT, the product category is duplicated across several orders, right? This product category is duplicated across several orders. So we need to update all of these rows. And there could be, in reality, there could be millions of rows that we need to update. Now, if you multiply it with every dimension, because there could be several dimensions that we could be using. For example, let's say product name changes, the region changes, right? Your update pipeline becomes a nightmare. So therefore, in a nutshell, you need to be able to justify choosing one approach over the other by understanding the real world impact of your modeling choices. The next one is slowly changing dimensions. So here's the scenario. Let's assume that the user upgrades their Spotify subscription from free to premium. So do you overwrite the old record or do you keep history? Yeah. So the question is, a user changes from free to premium. So do you overwrite the old record? Do you overwrite or do you keep history? If you overwrite it, that is SCD1. Yeah. So this is overwrite. So that is SCD1, simple, but you lose history. The reason for that is you can't answer how many users were there on the free tier 6 months ago because you've already overwritten history. Yeah. So this is what was there in the first case. For this particular user, this person was in the free tier and then we updated it to the premium tier and then we've lost history. Yeah. SCD2, on the other hand, what it does is it keeps both the records. Yeah, it keeps both the records. So the old row gets a valid 2. So earlier it was this case, which is user 42 was in the free tier. The person started the free tier from 2024, 1st of January 2024. Valid 2 equals null means that this is the current active tier. But the moment this person upgraded their tier, what is going to happen is that valid 2 is going to get updated to the date on which the upgrade happened, right? So this is going to close the record, right? It is going to close the record saying that the person was on the free tier from this date to this date. And then we are going to insert another row saying that the user is on the premium subscription. The user joined the premium subscription on this date, and valid 2 is null, meaning that this record is active. The user is currently on the premium subscription, right? So now you can very easily query the historical state of any dimension at any point in time. And this is really powerful in the sense that it's a standard approach for dimensions where history matters, right? And some examples could be understanding customer tier over time, the subscription plan, or the user geography over time. The next one is partitioning or optimization strategy. Yeah, broadly optimization strategies. So the most common and almost always correct default is partitioning by event date. Yeah. So time series data is almost always filtered by date in queries. So this dramatically reduces the amount of data that is scanned. Yeah. But also think about high cardinality filter column. If 80% of your queries filter by country or region, add that as a secondary partition key. So add that as a secondary partition key. The first one can be your event date, and then this one can be your secondary partition key. There are newer optimization techniques like liquid clustering, which actually removes the rigidity of fixing your partition column upfront. So with this approach of partitioning, you have to fix your partition column upfront. If you partition by date, but your queries start filtering by region instead, your partitioning strategy goes for a toss, right? It's no more helpful. And changing it means rewriting this whole data set again, right? So it basically means rewriting this whole data set again, and that's why newer techniques like liquid clustering becomes very handy. It removes the rigidity. So instead of creating fixed physical partitions, it dynamically reorganizes your data based on the columns you want to cluster on. So you can cluster on event date and region together, and let's say down the line, if your query pattern changes, you can just update the liquid clustering columns, and there is no need of a full rewrite. That's the beauty of it. Topic 4 is storage and file formats. This topic feels boring, but let me explain you with an example why this matters, right? So let's assume that you have a table with 200 columns, right? So let's assume that you have a table with 200 columns and a billion rows. Yeah. So 200 columns and 1 billion rows. Yeah. So the analyst frequently runs queries that only reads three of those columns. Yeah. So the analyst frequently run queries which reads only three of those columns. If your data is stored in a row-based format like CSV, the engine reads every single column of every single row, because there is no way to be able to skip the data that you don't need. But if we store the same data in a columnar format like Parquet, the engine just reads three of those columns. Yeah. And it simply ignores the other 197 entirely. So the same data, the same query, just because of the storage format, one scans the full table while the other one just scans less than 2% of it. So that is why understanding storage formats is really, really important. So we are going to talk about three things here. The first one is file format, row based and column based. We'll talk about Parquet and Avro. The second one is about Delta Lake and Iceberg and why do they exactly matter. And the third one is about database types, which is the relational and non-relational, and when should you choose either one of it. Yeah. So let's get started with the first one. And you can read about CSV and ORC, which are other formats, given that we are covering only Parquet and Avro, but they fall into the same bucket, which is either row based or column based. Yeah. So to give you a flavor of how row based looks like, let's assume that we have this table. Yeah. We have this table over here where we have order ID, name, revenue, city, and category. And this looks just as any other normal relational database table would look like. So in memory, this whole thing over here is this whole one row is stored as one chunk together, right? And similarly, it will be done for all of the rows. Yeah. But if you were to look at how it is stored in a column based format, it is stored differently. So all the order IDs are stored together. One column, all the data for one column is stored together. So you see all of the orders, they are stored together in memory. Yeah. Similarly, for name, revenue, city, and category, this is all stored together in memory. Yeah. So, first taking the example of column based, which is, let's say, Parquet. Parquet is the default for analytics workload and it is column based, right? So data is stored in a similar format that we have seen over here, right? Data is stored in column by column instead of row by row. So why does this matter? This matters because let's take this query. Select average revenue from sales where city equals Bengaluru. Yeah. So over here, it is looking at two columns. The first one is revenue. The second one is Bengaluru, which is the second one is city, which is Bengaluru. Yeah. So if your table has more than 200 columns, right, it is just going to pick these two up, right? So it is just going to pick up revenue and it is just going to pick up city. These are the only columns that are going to be read. Yeah. So the other 198 columns are skipped entirely, and this is called column pruning. And because the data is stored in a sorted format in Parquet files, you have the statistics stored at a file level. Yeah. The engine can skip entire files that don't match your filter. So Parquet is why analytical queries are fast and it can be used for anything that is read heavy and analytical, right? So I hope you understand why I mentioned read heavy, because it's very easy to pick up a column and then read just that chunk of the column over here, right? If you were doing this on a row based storage format, the same query, what you would have to do in order to compute the revenue is belonging to this row, this row, this row, this row, and this row. You have to end up reading all of the rows, right? And similarly, for figuring out which city equals Bengaluru, you have to read this row in order to be able to understand whether city equals Bengaluru or not. Yeah. So that is why in cases where your operations are read heavy, column based format work very well. Their performance is better. Now let's come to the second part, which is Avro. We covered Parquet. Let's come to Avro, and this is row based. Yeah, this is row based, which makes it faster for write heavy workloads. So the previous one was good for read heavy workloads. This is good for write heavy workloads. So think about what's happening when a streaming system is writing data. So every event, a write completed, a button clicked, or an order placed, they need to be written as a single complete record, one after the other, as fast as they come in, right? So a row based format like Avro is built exactly for this. Yeah. Each event that we see over here, let's say each button click, or let's say each order request, right? Each event is serialized into one complete row. All of the fields are packed together and then written in one shot. There is no overhead of organizing the data by columns. It just comes in, serializes the row, write it, and then move on. Yeah. On the other hand, columnar formats like Parquet are just the opposite. So they need to collect a large batch of rows first and then reorganize the data column by column before being able to write. Now, this reorganization takes time and memory, which is fine for a batch job running every hour or on a day-to-day basis. But this is terrible when you have, let's say, 10,000 events which is coming in, hitting Kafka, and each one needs to be written immediately. Yeah. Okay, so why don't we just dump Parquet files in S3 and call it a day? Yeah. So a lot of early data lakes did this exactly. Yeah. So a lot of early data lakes did this exactly. Now here's the problem. When you dump raw Parquet files, yeah, when you dump raw Parquet files in S3, yeah, there is nothing that is managing them, right? They are just files sitting in a folder. And what happens when there are two Spark jobs trying to write to the same table at the same time. Yeah, they can overwrite each other's data. Your records get corrupted or go missing, and nobody gets an error. And that is what no acid guarantee looks like. And that is what no acid guarantees look like. So I hope you understand the problem. There is no layer on top of Parquet file that is managing them, and you can have multiple jobs which is writing to the file. Both of them can override each other's data can get corrupted, data can go missing, and none of us are going to get an error, right? So it all happens in silence, and this is what no acid guarantee means. There is also another problem, which is there is no schema enforcement. So there is no schema enforcement. And what this means is if somebody accidentally writes a string into a column that's supposed to be an integer, it simply goes in. So you won't find out until a pipeline downstream breaks. Yeah. And then there is this third problem. There is this third problem, which is the small file problem. Yeah. Small file problem. So when you're reading streaming pipeline, when your streaming pipelines are writing thousands of tiny Parquet files, each one a few KBs, Spark has to open and read every single file. Now, this process of opening and closing the file, the IO operation involved, has a lot of overhead involved, right? Which makes the queries slower than if you than it would have had to read one big file, right? So imagine reading one big file, and then there are IO operations for opening and closing the file versus doing it on thousands of small files, right? Opening them, closing them, again opening them, closing them, and doing it for several of such files, right? So Delta Lake and Iceberg and Hudi as well solves all of these problems. So it has many features like ACID transactions, multiple writers without data corruption, time travel, query or table as it existed yesterday, last week, last month, schema evolution. So basically, it helps you add a column without breaking your existing pipeline. And then optimize command in Delta, which runs compaction. It basically takes all of these small files and optimizes it into one large and more efficient files, right? And that is why these open table formats are really important. So I've made a detailed video on Delta Lake, which is a 5 hour long deep dive video. If you're interested, do watch that topic. Now, the last thing I want to discuss for storage and formats is basically database types. And this is very popularly asked in system design interviews, as in when should you choose a relational over non-relational databases, right? So when you're solving a problem and when you have an opportunity to choose a database, you will have to decide between either of these two, right? Either relational and or non-relational, right? So you choose relational when your data is structured, when you have clear relationships, when you can think of and evaluate that you have clear relationships between different entities, and you need strong consistency, right? You need ACID compliance, and you have complex queries in place in order to be able to answer your business question. That is when you choose relational databases. Non-relational databases, you choose them when you need flexibility over the structure of data, when you have semi-structured or unstructured data or rapidly evolving data, right? And you can trade strict consistency, right? Strict consistency, something like ACID compliance for speed and availability, right? So something like logs or social media data or IoT data, right? So that is where you would want to choose a non-relational database. Okay, so now everything we've covered so far, pipeline design, data modeling, storage, all of it, yeah, all of it assumes that the data flowing through is correct. But anyone who has worked in production knows that that is a very dangerous assumption, right? So sources change without any warning, fields go null, row counts drop, and the worst part is unless you have placed thorough data quality checks, the pipeline is going to run successfully, write bad data to the tables, stakeholders are going to make incorrect decisions on it before it is even noticed and corrected. Yeah. So this is the problem that we are trying to solve with data quality. And we are going to talk about three topics. The first one is data quality dimension. The second one is data contracts. And the third one is observability. Okay, so when we talk about data quality, we are not just saying whether the data is good or bad. There are specific dimensions that we need to check for, right? And we are going to talk about data quality dimensions, right? So we should divide our checks into each of these dimensions, right? The first one is completeness. Yeah. And by completeness, what I mean is whether all of the data is there or not. So if your order table usually gets 10 million rows in a day, and today it has got 7.5 million orders, something upstream broke. Yeah. Or if let's say your customer email column is 40% null, that is a completeness problem. The second dimension is accuracy. Yeah. So accuracy simply means whether your data is correct or not. So an order amount of negative 500 is incorrect. A delivery time that is before order time is impossible, right? So these are things that your source system might allow, but your pipeline data quality logic should never allow. Yeah. The third one is consistency. So consistency simply means whether the same data agree across different systems, right? If your order table says the total revenue for March is $2 million, sure, but your payment table says that the total revenue is $1.8 million, something is off, something is broken, right? So it simply means whether your data agrees across system. Yeah. Point number four, which is the fourth dimension, is freshness. Yeah. So freshness simply means whether the data is current enough or not. Is basically says that the SLA says that the dashboard refreshes every day. Yeah. But the last update was 3 days ago. So the SLA says the dashboard refreshes every day, but the last update was 3 days ago. Therefore, we are making decisions on stale data. And the last one is uniqueness. Uniqueness simply means whether there are duplicates or not. Your pipeline retried after a timeout and it wrote the same batch twice. Now every metric is inflated. Yeah. So these are some of the most important dimensions that we should always consider when we are writing our data quality checks. And each of our checks should fall into one of these dimensions, right? So these dimensions give you a foundation for building your data quality checks. And instead of like vaguely saying that you're going to add some checks, you should exactly say which check are you adding and in which dimension it is going to land. Now, all of these checks that you see over here, right? All of these checks that you see over here, these checks catch problems after the data has entered our systems. But what if you could catch structural issues right at the point of ingestion, right? Right at the point of ingestion. And that is exactly what data contracts do. That is exactly what data contracts do. Yeah. So data contract is basically a formal agreement between a data producer and a data consumer. It is going to define what exactly will the producer send, basically the schema, the data types, which fields are required, and what values are allowed, right? So to keep it simple, you have a data producer, you have a data producer, and let's say this is a microservice. we are consuming data from this microservice, right? And the consumer is basically my pipeline. So there is going to be a contract which is going to define what exactly is going to be accepted from the microservice, right? So let's take an example. Let's say that with a data contract we are going to agree upfront that the payload that this microservice sends, it is going to have order id as a string, amount as a decimal, timestamp in an ISO format, and the schema won't change without a version migration and a 2 weeks notice, right? So if they want to change the schema from v1 to v2, and whatever we agreed, let's say the order id, right, the amount and the timestamp and all of those, right, if this is supposed to change from v1 to v2, there has to be a 2 week notice so that the migration can take place. Now if they break the contract, it is flagged even before the data enters your bronze layer, right? So let's assume that this pipeline was putting data in the bronze layer. This is going to fail and it is going to be flagged even before the data enters the prompt layer. So in practice, data contracts are enforced through schema registries for streaming data like Avro with a Confluence schema registry, and through schema validation tools like Great Expectations. Yeah. So the key point is data contracts shift quality left. Yeah. Instead of catching bad data in your pipeline, yeah, instead of catching bad data in your pipeline, you prevent it right at the source. Now data quality catches problems with the data itself, right? But what about the pipeline that is producing the data, and how do we know that it is healthy? And that is where pipeline level observability comes in, right? So that is where pipeline level observability comes in. Yeah. So we check if our DAG is running, did it fail, or how long did it take? Is it taking 3 hours when it should, let's say, take only 40 minutes, which might mean that either the data volume has spiked or our cluster is undersized. So all of this can be monitored through an orchestration tool, and let's say you can use Airflow, Prefect, Dagster, and these are easily available through their built-in metrics, yeah, or through other tools like, let's say, Datadog or CloudWatch if you're on AWS. Okay, topic 6, the final piece, which is pipeline resilience. So what happens when things break? And they will break, right? How do you rerun your pipelines without duplicating data? How do you backfill years of history if your business logic changes, right? And these things are bound to happen, right? Business logic is bound to change over time. How do we scale and deploy pipelines without bringing production down? Yeah. So let's start with what I call the golden rule for data pipelines, and that is idempotency. Okay, idempotency. So here is what it means in simple terms. So if you run your pipeline twice with the same input, you should get the exact same output. Yeah, no duplicates, no missing data. Run it once or run it 5 times, the result is identical every time, right? And this actually sounds obvious, right? But getting it right in practice takes intentional design, right? You need to intentionally think about it and then design your pipelines and code in that way. So one of the ways you can achieve idempotency is by using a merge instead of insert for incremental loads. Yeah. So you can use a merge statement instead of insert for incremental loads, right? So merge is going to update a record if it exists, or insert if it doesn't exist, whereas an insert is just going to add rows. So if you run an insert twice, you will have duplicate, but if you run a merge twice, you will end up with the same number of records. Next one is backfills. Yeah, backfill. And what exactly is a backfill? So to simply put it, it is when you need to rerun your pipeline over historical data that has already been processed. And this actually happens quite often. Yeah, it happens quite often with data engineering team. So let me give you two real scenarios. Scenario one is, let's say, where you find a bug. Your pipeline has been calculating delivery duration as delivered at minus created at. Yeah. Now, instead of calculating delivered at minus dispatched at, so it has been wrong for, let's say, 3 months. Every report, dashboard, and metrics based on the delivery time is incorrect. So you fix the code, but now after fixing the code, you need to rerun your pipeline and you need to reprocess 3 months of data with the correct logic. So that's one scenario. The second scenario could be your company has always counted total orders as every order placed. But now the business team decides that cancelled orders within 24 hours, they shouldn't be counted. And they want the total orders to mean that orders that were only fulfilled. Yeah. So going forward, your pipeline applies the new filter, but the old reports are overstating orders. Yeah. So we simply need to reprocess the old data. First of all, fix the code, make changes to the code, and then we need to reprocess the old data with the updated definition. Yeah. So if your pipeline is idempotent and if you're using Delta Lake or Iceberg, you can directly overwrite the affected partitions. Yeah. So let's say if from day X to day Y, right, you have partitions which is 2026 0101 until 2026 0401, you want to overwrite all of these partitions. You can directly overwrite all of the affected partitions, right? Because these table formats support ACID transactions. The write is atomic, and by atomic, what we mean is that either the write completely happens, or if it fails in the middle, nothing happens, right? Everything is rolled back. So either the entire partition gets replaced or nothing changes. If the job fails halfway, the old data is still intact. And your downstream consumers never see partial data. So you just rerun the pipeline for those affected dates, and it simply overwrites the partitions cleanly. Now let's talk about schema evolution. Yeah, let's talk about schema evolution. So at some point, your upstream sources are going to change the schema. Yeah, it is not going to happen every day, but at some point in time, it will happen. And if you are not prepared for it, it will break your pipelines downstream. So here's what it looks like in practice. So let's say the payment teams adds a new column, which is a discount code to their order event. Or let's say the mobile team renames user location to device location, or an API you are ingesting from silently changes a field from an integers to a string, right? Now, none of these are very big changes, right? None of these are dramatic changes, but any one of them can cause your Spark jobs to fail and your tables to write garbage or your dashboards to show incorrect data. Yeah. So the question is, how do you design your pipeline so that it is able to handle these changes gracefully? And the approach is to be flexible at the bronze layer, but be strict at the silver and gold layer. So be flexible at bronze and strict at silver and gold. Yeah. So at bronze, you simply accept everything as is. Whatever your source code sends, you land it, you don't validate it, you don't enforce, or you don't reject anything, right? If a new column shows up, it simply gets added. And Delta Lake supports this option with the merge schema option, right? With the merge schema. Delta Lake supports this using the merge schema option. So it automatically accommodates new fields without failing the pipeline. And again, this is intentional. Your bronze layer is your safety net. Yeah. So you want every piece of information to land over there, your raw data to be captured, even if the shape or form changes. Yeah. But by the time your data moves from bronze to silver and from silver to gold, you enforce a strict schema, right? You enforce a strict schema. And why do we do so? We do so because the analyst, our dashboard, our ML pipeline, they all depend on it. They expect, let's say, the order amount to always be decimal. They expect the user ID to always exist. So if a new column appears upstream, it lands in bronze automatically, but it doesn't reach silver until the pipeline code explicitly maps it, right? Maps it, validates it, and decides where it belongs. So schema evolution absorbs changes at the bottom and then enforces consistency at the top. So now we've covered all of the principles and concepts, right? So let's take all of them and let's put everything that we've learned so far, that we've covered, into action. So I'm going to walk you through a complete system design interview question right from the start to the end. Yeah. So we are going to cover all of the topics that we have learned so far. However, please keep in mind that the interviewer might take a wide and then a zoom approach. So they might go deep into some topics that might be of more interest to her. So, for example, let's say pipeline design or data quality or data modeling, right? Based on their interest, they might want to deep dive into some of the topics more than the other. So, here's the question: design a real time analytics pipeline for a food delivery platform like Uber Eats, Zomato, and Swiggy, right? So we have to design a real time analytics pipeline for a food delivery platform like Uber Eats, Swiggy, Zomato. Yeah. So the platform needs to track different things like order events, delivery metrics, and provide both real-time operational dashboards for restaurant partners and daily aggregated business reports for the executive team. Yeah. So basically, this pipeline has two kind of consumers. The first one is basically those restaurant partners who want to see metrics like what is my total earnings as of today, what are the total number of orders that we have delivered so far, what is the pending orders, right? So there is an operational dashboard. Yeah, there is an operational dashboard requirement, and then there is a daily business report requirement. Daily business report requirement. So this is the first one, and this is the second one. Yeah. So the second one is basically for more for the executive team, the finance team, so that they are able to look at metrics on a day-to-day basis. So I hope the question is clear. All right. So you've heard the question, and I want you to resist the urge to start solving it immediately. Yeah. I know it's tempting, but the best thing you can do in the first 5 minutes is not to design anything. Yeah. So just say, I'd like to ask a few clarifying questions before I start. And trust me, honestly, the interviewer is expecting this. Yeah. In fact, they are waiting for it. So if you skip it and jump straight to the tools, they will let you do so. They won't stop you, but they are already noting that you didn't think about the problem first, right? So here are the first few questions that I will ask. Yeah. So the first question is, who are the end users? Who are the end users, right? And this is basically, some part of it is answered in the question itself, right? What we've understood is there are two groups. The first one is those restaurant partners who need to see their live orders, and an executive team who needs business report. So we understand that there are two audiences over here, and they have completely different SLA needs. Yeah. So the first one is restaurant partners, and this one is the executive team. Yeah. The second question that we should ask is what exactly are those latency SLAs, right? So, what exactly are those latency SLAs? Yeah. So for the restaurant dashboard, it could be under 2 minutes end to end. Yeah. And for the executive dashboard, the daily batch delivery is totally fine. Yeah. So we can simply say that for this one, less than equal to 2 minutes is fine. And this one day is completely fine. Yeah. So that would be the second question that we would ask. The third one is what is the approximate data volume? What is the data volume, right? And let's say the answer is we have 5 million orders in a day. Yeah, we have 5 million orders in a day, and during peak load dinner rush between 7 to 9 p.m. it is around 500k orders per hour. During peak load it is 500k orders per hour, right? And that is an interesting metric. The other question that we can ask is what are the events that we are tracking, right? So are the events what are the events that we are tracking? And this could be, let's say, 6 event types. The order placed, and then after the order was placed, the restaurant confirmed the order. So first one is order placed, restaurant confirmed, driver assigned, driver picks up, driver delivered, and then if the order was cancelled, order cancelled event, right? So 6 events, they would happen chronologically, which is order placed, restaurant confirmed, driver assigned, driver picked up, driver delivered, or order cancelled. Yeah. And then finally, what I would also like to ask is what is the data retention? So let me write 6 over here first. Yeah. And for data retention, let's say we have 2 years for analytics and 90 days for real time serving. So we have 2 years for analytics and 90 days for real time serving. Yeah. Now remember what we covered earlier, back of the envelope calculation, and this is where to apply it, right? So we've got our requirements, we've got our volume estimates. Let's quickly run the math so that we start designing and our choices are backed by actual numbers. Yeah. So what have we said earlier? We said that there are 5 million events, 5 million events per day, right? We said that there are 5 million events per day and there are 6 event types, right? So there are 6 event types, correct? And those 6 event, just to reiterate, they are basically order cancelled, restaurant confirmed, driver assigned, driver picked up, driver delivered, or order cancelled. Yeah. So this basically gives us 5 million events into 6 events. This is basically 30 million events in a day, right? So this is 30 million events per day. Now let's get the per second rate. So 30 million events, which is this number over here, and per day is basically 24 into 60 into 60. Yeah. So if you do the calculation, roughly this is going to give you this number 350. Yeah. So this means that we are getting 350 events per second. Yeah. So we are getting 350 events per second. But remember, we also said during the peak hour, there are 500K orders, yeah, during dinner rush. So we should also take that into consideration. So 500K per hour, and therefore this is also going to have 6 events. This means that 500,000 into 6 events, which is 3 million, and this is basically per hour, right? So if we take 1 hour, which is 60 into 60 seconds over here, this is roughly going to give me 833 events. Yeah, so this makes something very clear. The range, the range of events could vary somewhere between 350 to 833, right? Roughly on an average, the number of events per second could be somewhere between 350 to 833. Yeah. And this is something that is very manageable for Kafka. So this is something that is manageable, very manageable for Kafka. Even a modest 3 broker cluster can handle this easily. We don't need an aggressive partitioning strategy over here. Something like 6 to 12 partitions gives us a good parallelism for our Spark structure streaming consumers. Yeah. Now let's think about storage. So now let's think about storage. So each order event, let's say, is a JSON. So each order event is a JSON, and this basically contains attributes like order ID, event type, timestamp, restaurant ID, driver ID, customer ID, coordinates, and all of that, right? So again, let me just note it down quickly: order ID, the event type, timestamp, event type, and all of those, right? And let's say that this is 1 KB. Let's say that this is 1 KB in size per event, right? This is again an assumption, and this is something that we need to confirm in communication back and forth with the interviewer, right? So based on what the interviewer says, tune this number. Yeah, so there are 30 million events in a day. Yeah, and 1 KB of data per event. This basically gives me 30 GB of data per day, right? So this gives me 30 GB of data per day. And if you remember, when we talked about retention, the interviewer said that it should be 2 years of retention. So this should be something like 30 GB per day into 365 into 2. And this leaves me with somewhere around 21,900. So roughly this is 22 TB, right? So this is roughly 22 TB of data in the bronze layer before compression. If you add Parquet compression on top of it, which roughly gives you 2 to 5x of compression. Yeah, so it is somewhere going to be between 4 to 11 TB, right? This number is going to go down 2 to 5x, and it is going to be 4 to 11 TB, and we are looking at 4 to 11 TB on disk, and this is something really manageable for S3 or ADLS, right? And for the now let's come to the real time serving layer. So for the real time serving layer, which is, let's say, Redis in our case, let's think about what data actually sits in Redis. So the restaurant dashboard doesn't need every raw event. Yeah, it doesn't need every raw event. It needs a small set of pre-computed metrics per restaurant. So things like current active orders, average delivery time in the last hour, orders completed so far. Yeah, so let's say that is roughly 10 to 15 field, right? So let's say that it is 10 to 15 fields per restaurant, correct? If we have 50,000 active restaurants, and again, confirm this with the interviewer, let's say we have 50K active restaurants. We have 50K active restaurants, and each restaurant dashboard records is 1 KB of data. Yeah, each restaurant's dashboard records is 1 KB of data. That means we have 50K into 1 KB, which is just 50 megabytes of data, right, at any given time. So a single Redis instance can hold this in memory very easily. So this is exactly why we do back of the envelope calculations, right? So now we understand that our Kafka setup, based on the calculations that we have done over here, based on the calculation that we have done over here, the Kafka setup is very manageable. That is number one. We have also understood that our storage cost, right, and our storage volume is also something very predictable and manageable. And lastly, for the serving layer, Redis handles the serving layer comfortably, right? And most importantly, we now know the scale of this problem, and it's moderate, it's not massive. So now let's move on to the next part, which is pipeline design. Okay, before we step into pipeline design, I want you to internalize this, right? So we are not building two different systems. We are building one data platform with two consumption patterns, right? So we are building one data platform with two different consumption patterns. The first one is for those restaurant partners, and the second one is for the executive team. Yeah. So the source of truth is one, basically our event stream. Everything else is a shaped view of that stream, right? Optimized for a specific consumer latency and query pattern. So basically what I want to say is we have one event stream, which is Kafka, and here is where our events are flowing into. And there are two consumers. The first one is the streaming path, right? And the second one is the batch path, correct? So this one is for the restaurant partner dashboard, right? And this one is for the executive report. Yeah. So the restaurant dashboard needs data within minutes. The executive reports needed by next morning. So we are designing a Lambda style architecture with two parallel paths. Yeah. So the keyword is Lambda style architecture, right? We are designing a Lambda style architecture with two parallel paths. The first one is going to be streaming path for real-time operations, and the second one is the batch path for historical analysis. And this is how it is going to look like. Yeah. So path A is going to be the streaming path. Yeah. Path A is going to be the streaming path. Order events are going to come in. They are going to hit Kafka, and this is going to be partitioned by restaurant ID, so that events for a given restaurant say ordered. Spark streaming is then going to pick all of this up. It is going to calculate the running metrics, and then it is going to write the result to a NoSQL database. And this is connected to a live restaurant dashboard that the restaurant partners can see. Now, during the interview, you can possibly face some questions, and it is worth digging deep into this, right? So, how are the metrics going to be calculated? Yeah. And what exactly are those metrics? Now, path B is the batch path. Yeah. So batch path is, it is getting the same event from Kafka, which is getting synced to S3 or ADLS as raw Parquet. Yeah. So if we were using AWS, this is going to be MSK, which is managed streaming for Kafka, and then you would need Firehose in between, which can read the events from here and then dump it over here, right? And then once the data lands in S3, you can have a whole data pipeline over here, which basically takes the data from bronze, cleans it, puts it in silver, and then creates aggregated records in gold, which can then be picked up by the executive team and then be shown on the daily dashboard, right? So now we have designed a robust pipeline. Yeah. So an interesting thing to note is after you've designed this architecture, right, the interviewer might want to dig deeper into some of the topics, right? So for example, they might want to dig deep into Kafka over here, right? And there can be some questions around, let's say, exactly once versus at least one semantics. So those can be one type of question. The second one could be, how do you handle, let's say, the partitioning strategy, retention, log compaction, things like watermarking, what how do you deal with late arriving data and all of that, right? So all of that can come over here if the interviewer wants to dive deep into Kafka, right? Some other interviewers might want to dive deep into, let's say, Spark. Yeah. So in Spark, they can ask you questions like Spark internals, things like AQE, things about, let's say, the query plan at a high level, right? What does shuffling mean? What are the different kind of join strategies and how do they differ? How would you want to store your data in this in all of these layers, right? What kind of uh, data optimization and storage strategies will you apply? Will you apply things like partitioning, bucketing, reordering, liquid clustering, and all of that, right? So there can be a very deep discussion based on the areas that the interviewer is interested in once you come up with this architecture. Yeah. So I would suggest you to brush up your knowledge about, say, things that you have worked on the past. If you worked with Kafka, brush up your knowledge, right? Strengthen your basics about Kafka, strengthen your basics about Spark. Let's say if you've used Delta or Databricks, try to understand it in more detail so that you're able to answer questions and you're able to explain what you've already done, right? You're able to reason and back your answers with logical explanations. Next, we are going to use a medallion architecture with 3 tiers. Let me quickly erase this out. Right? So these 3 tiers are basically going to be the bronze, silver, and the gold layer, right? So bronze, as we know, is going to be the raw ingestion layer. Order events are going to land at JSON from Kafka, and one order event could be something like this, right? So it will contain things like the order ID, what is the event type. The event type is order place. When was the event? uh, when did the event happen, which restaurant to which was the order placed, which customer placed the order, and things like this, right? So this is basically going to land in the bronze layer, right? We don't clean anything here. This is your immutable source of truth. Yeah. Now next up in the silver layer, this is where we are going to build our data model, right? Which are basically our facts and our dimensions. Yeah, basically our facts and dimensions. The most important ones are fact orders, dim restaurants, where all of the restaurant details are going to be stored, right? And then dim drivers. Dim drivers. Yeah. So these three are going to be the most important tables. For fact orders is basically going to contain details like your order ID, restaurant ID, from where did the restaurant, the order come in, right? The driver ID, the person who is going to deliver the the order. Yeah. Order placed at, delivered at, cancelled at, total amount, delivery duration, right? Things like that. So this table can either be partitioned or liquid clustered by the order date. Yeah. Similarly, for restaurant, it's going to have the restaurant ID, the name, city, and let's say another column such as active since. And the driver table can have the driver ID, the name, city, rating, and the vehicle type. Yeah. So there can be other tables as well over here in the data model. For example, let's say fact payments, fact subscriptions, dim food items, and all of that. But let's keep it simple to basically serve as an inspiration to build the final one, right? And finally, in the gold layer, we are going to have two tables, right? Aggregated tables, which is basically the daily restaurant metrics, right? Daily restaurant metrics, which is over here. Yeah. And for the restaurant dashboard, actually, we'll only have just one table, right? The live one is going to be served from here, and the daily one is going to be built in the gold layer, which is going to be served over here. Yeah. On the storage, we are going to use Parquet over here, and then all of the rest from here to here, it is going to be the Delta format. Yeah. Okay, so the next thing that we should think about is data quality checks. Yeah. Let me quickly erase all of this over here. So the first thing, as we studied earlier, is we should apply data contracts at the schema registry so that we are able to find out malformed or incorrect records which are not correct in the structure right at this point. Yeah. So that's the first thing that we should do. The second thing is applying data quality checks at the bronze layer. Yeah. So what you can do is basically we can check things like, let's say, event type. So this event type is always going to be limited by certain types of valid values, right? So this can be any of order placed, driver assigned, order picked up, order delivered, or order cancelled, right? So we can check for this, right? That's one of the checks. We can also check whether this combination of order ID plus event type is not duplicated, right? So if it happens, we just log, we don't drop. Yeah. So this is a weird case that I'm talking about, right? Ideally, it shouldn't happen, right? But of course, these are what data quality rules are meant to detect. And then there can be other checks as well that we can place over here. For example, checks on customer ID, they should not be null and all of that, right? By the way, a very important point to note is that all of these checks are going to fall in those dimensions that we discussed. So similarly, you can apply checks on the silver layer. Some examples are going to be, the most simplest example is the null check on different kind of attributes. The other one is referential integrity checks, right? Referential integrity checks. What this simply means is that every restaurant ID in, let's say, the fact order table. So we created a fact order table over here. Every restaurant ID in the fact orders table, they must exist in the dim restaurants table, right? So orphaned orders means that a restaurant was never onboarded. Yeah. The other one that you can also apply is based on certain kind of business rules, and several such business rules might exist, right? So let's say the delivery duration in minutes. The delivery duration in minutes should be between 1 and 180, right? A more than 3 hour delivery duration is, let's say, a data error. Yeah. Some other checks that you can apply is time-based consistency logic. So for example, picked up at must be after order placed at, right? And delivered at must be after picked up at. So these are also some kind of sense checks, right? So pickup can be only after the order has been placed, and delivered can only be after the order has been picked up. And a few other ones that you can also apply is some kind of volume based checks, right? So what we basically do is we compare the current day's number of rows with, let's say, the last 7 day rolling average, right? And we see whether it is going out of proportion or under proportion, right? And then we flag based on the results. Yeah. So all of these checks again are going to go in those dimensions that we discussed, and I leave it to you as homework. So that is how we can create data quality checks for the silver layer. Now taking some examples of the gold layer. In the gold layer, we are going to aggregate all of our data, and we can apply some kind of aggregation sense checks. For example, let's say the cancellation rate percentage must be between 0 and 100. Yeah, average delivery minutes must be positive, and it should be a logical value. It shouldn't be like in 4 hours, 5 hours. That number has to be decided by the business. Yeah, so again, this is how you can place meaningful data quality checks at the bronze, silver, and the gold layer. Now, the last part is about scalability and operations, and I will leave you with four things that can be discussed with the interviewer in this section, and something we've already discussed in detail before. Number one is going to be your backfill strategy, right? Is going to be your backfill strategy. So what if the aggregated table that you have created over here, some logic changes and you need to refresh the values over here? So how are you going to make sure that you can seamlessly rerun the pipelines with the updated logic for a given start and end date? Yeah. Number two is going to be idempotency. Yeah. So how are you going to make sure that your pipelines can run n times with the same inputs and it will produce the same output? And this is a non-negotiable requirement. And the last one is schema evolution. So basically, bronze should use schema on read, yeah. And then silver should enforce a strict schema, right? Silver and gold should enforce a strict schema, right? With merge schema enabled for any new addition. Yeah, and that's it. Yeah, that's it. So we've designed a complete system starting from the requirements, data model, pipeline, storage, data quality, operational readiness, scalability, and operations, right? So we've discussed all of this, and that is exactly the flow you should try to follow as much as possible in an interview, right? And it's completely okay if you're not able to cover every topic that we've discussed over here in details. That is completely fine, but if you're able to show this structure, it tells the interviewer that you are very well rounded in your thinking. Yeah, okay, so let me leave you with this. The candidates who fail system design interviews aren't the ones because they don't have knowledge about Kafka or Spark structured streaming, or let's say delta tables, right? Of course, if you don't have knowledge, you will fail the interviews. What I mean to say is that people who have complete knowledge about these tools are still failing interviews, right? And they fail because most of them lack a structure. They jump straight to the tools without understanding the problem in detail, without spending a lot of time on requirements gathering, right? They design for the happy path without thinking too much about the failures, the problems that could come up in their design. Yeah, and the candidates who pass, they basically slow down. They spend a lot of time with the interviewer asking questions, drilling down on requirement gathering, right? They ask questions and make the reasoning visible. What I mean by making the reasoning visible is that they're very vocal and they shout out when they have to choose one technology over the other, right? When they have to choose one path over the other. Yeah, they highlight about the pros and cons of one over the other, and this is very important. It's very important to be able to reason your choices, to be explain your thinking about choosing one approach over the other, right? So that is what I mean by making your reasoning visible in front of the interviewer, and that is the real difference. If this was useful, please don't forget to like, share, and subscribe to my channel. I put out deep dive data engineering content, the kind of stuff that actually moves the needle in your career. I hope this was interesting to you, and I will see you in the next video.